simplest form of this function. Okay. So remember when we're talking linear functions, you guys might like y equals mx plus b the most. Okay? So in that format, this is your parent function. Okay? Does anybody know another name for this function? So think about it. Every time you, No, but you're thinking forms of lines. That's good. Okay. So think about what happens here. What do all the points look like for this line? So you plug in an x value. Say I plug in 3 for x. What do I get for y? The same value, okay? So oftentimes, they call this like the identity function because you plug something in and you get out, like John said, the exact same value, okay? So take a second, because remember, these count as kind of an important portion of your notes, right? Their own separate section.
Whatever x equals y equals also.
Good. All right, so he said, so if you don't have a good explanation, you can copy his. It is known as the identity because whatever x equals, y equals also. Sorry, I actually have really messy handwriting, as you can see. When I used to take notes, I can't read notes. All right. So the next thing we want to put on is we want to put on the graph. Okay. Any idea what the graph of this line is going to look like? So somebody walk us through, because on the back side of this, you have a bunch of problems that you're going to eventually have to graph. They're written in different forms, so we're going to want to pay attention to where the information is. If this is considered, this actually could be considered slope-intercept form or point-slope form. Okay, we'll get to those in a minute. Somebody tell me how you would go about graphing this. What is your normal procedure for graphing the line? All right, John, go for it. Good. Okay, and where is he going to start this pattern of going 1 over and 1 up? 0, 0. Why 0, 0? Because you don't have a value. So if you're thinking y equals mx plus b, the b is the begin spot, right? It's your y-intercept, and that's the place where you start your graph from that point on the y-axis. If this is y equals mx plus b, there is no plus b. If you're not adding anything on, you're technically adding 0. So our starting spot on the y-axis is at 0 on the y-axis. Okay. And so how did he know that he needs to go over 1 and up 1? How is he determining that? Why not 5? Why not over? So there's no number. So what number is here in front of x if there is not a number? 1. So that's what he's getting is over 1, up 1, okay? And if we continue that pattern, 2 points is enough to draw a line, but I can't draw a straight line by myself, so I'll continue the pattern a lot. Remember, you also could go over -1 and down -1 because a negative over a negative would divide out to be a positive slope still. So you could do 2 negative movements to make that positive also. So you'll get this line. So that's our parent function. When we start changing the numbers in our equation, our line changes, right? If we start adding more stuff over here or subtracting it, we shift our line up or down, right? Because the y-intercept would change. And if we start changing the slope right here, okay, those are kind of like stretches or compressions. Kind of hard to see with a linear function, so we don't have to use that exact language. But it changes the slope to be steeper or less steep or negative direction. Okay? All right, so let's talk domain and range. Does anybody feel like they know the domain of this function? Yeah. Good. All real numbers. Can anybody explain how he knows that this function has a domain of all real numbers? Yeah. Good. It goes on forever. And are we looking at x values or y values when we're focusing on domain? The x values. So you're really asking yourself, what x values can I plug into this function and I'll be able to calculate an answer? Okay, so from the graph, I have this teacher friend and she's much more fun than I am. So she actually uses, I know this is silly, but she uses JZ. And Spider-Man, she literally has a JZ finger puppet. I don't know. I told you guys she's much more fun than I am, okay? So when she's talking about domain, she talks about like Jay-Z being on stage because he would be like moving across the stage at different points in time. I don't know. Never seen the man in concert. Not my most often listened to music, but you know. So if you're moving to the left or to the right and your graph is your stage, would he ever fall off the stage? Is there a hole? Is there an ending? Is there a beginning as I move from left to right? No. Okay? So if there's no holes, no ending, and no beginning, then everything is covered, right? Which is where we get the all real numbers kind of thing. Okay, so our domain is all real numbers. So that means algebraically, anything you plug in here, we can calculate the answer. And graphically, it means if you pick any x value on the x-axis, you will be able to see a point on the graph lined up with that number. There are no numbers that it fails for. Okay? All right, what about the range? What are we focusing on now if we're trying to determine the range? The y value. So this is where her Spider-Man finger puppet comes in because Spider-Man can like scale buildings, right? But if there's like an open window and he tries, that would be bad. Okay. All right, so we're now focusing up and down. So if this is like Spider-Man scaling his building, are there any holes, open windows? Does it end? Does the building stop? Okay. Does he hit the floor anywhere? No. I can go forever up and forever down, right? I'm really traveling along the same thing. I'm just changing the way I'm thinking about my perspective. So again, because there's no place where the graph stops or has a hole vertically, that means the same thing it meant for x. You could pick any y value, and there's a place on the graph where there's a point that has that y value. So that means you have every y value covered. None are skipped or not included. So our range is all real numbers. Anybody have a question about domain or range? I know the Jay-Z Spider-Man thing is funny, but sometimes it helps people remember, so throw it out there, right? If I was really fun, I'd have a finger puppet like her and do it. It's just not my personality. It's just not there. Okay. Any questions about those things? No? All right, so we have our parent function. We understand why it's called the identity, and we understand the domain and range of the function. All right, so right below this, we talk a little bit about domain and range and things that might not be the same. So basically, you could have all these lines, right, on graphs traveling different directions. What would the domain or the range be of any of these lines that I'm drawing up here? All real numbers. Do they have any breaks or stopping points horizontally? No. Vertically? No. So most lines have a domain of all real numbers and a range of all real numbers. But there are two exceptions. Okay? Can anybody think of a line that would not have a domain of all real numbers? Huh? When it goes across. Okay, so there's these two. What about when it goes across like this? And what about when it goes across like this? Okay? In each of these cases, one of them, the domain or the range, is still all real numbers, but one of them has been very stifled and stuck at one value. Okay? This line right here, does anybody remember the equation for horizontal lines? Y equals good, because if this is on a graph where this is my x-axis and this is my y-axis, and let's say it's crossing through 2. Yeah. Every point on this line, no matter where you pick, I don't know what the x-coordinate is because I didn't scale it, but I know the y-coordinate will have to be 2. So the equation of horizontal lines, they cross through the y-axis at that number. They all have the y-coordinates. They are y equals a certain number. Okay? So domain. Is the domain still all real numbers? Can Jay-Z still move across the stage without whatever? Can you still plug in any x coordinate that you want for the points up there? Yeah, the x can be any number along the way, left or right. So the domain there is still all real numbers. Let me make a little note of this. So the domain is still all real numbers. But what is the range of this function? Can Spider-Man go up and down? No. Does he change height at all? No. Every point on this line has one single numerical output, and it is what? 2. That is it. The range is literally just the number 2. No points exist on this line that don't have the number 2 as the y value. That is the only value that is accepted. So that is our entire range. Okay? So here, our vertical line, what is the equation of our vertical line going to be? This is my x-axis. This is my y-axis. Let's say it's crossing through -2. Okay? What's the equation of that vertical line going to be? Good. X equals -2. Because it crosses the x-axis at -2, and every point on this line has an x-coordinate of -2. Okay? So that's a consistent thing about that line, and that's why they name it x equals. All right? What would be the domain of this line? Is it all real numbers? Can you move from left to right and capture every x value? No. So then what are the limitations? X can only be equal to what? -2. So the domain is literally one number. All x can be is -2. But what about the range? Now thinking about it vertically. Okay. Can you capture all the values? Is there any limitations? So are there any limitations? No, the graph doesn't stop vertically. It goes forever vertically. There's no holes or anything like that. So the range would still be all real numbers. So these are the two exceptions. Horizontal lines still have a domain of all real numbers, but their range is just equal to whatever value they're stuck at. Okay? Vertical lines, the domain is equal to whatever value they're stuck at, but the range is still all real numbers. Every other line, because it's kind of slanted at some point, has some slope, will be all real numbers left and right, all real numbers up and down. So domain and range, both all real numbers. Okay? So go ahead in your groups and take a second and write your own equations. So don't use y equals 2 and x equals -2, but give 2 examples. So one should be of a horizontal line and one should be of a vertical line that don't have domain and range that are all real numbers in both places. Okay? So just take is one example, okay, of an equation of a line that does not have domain and range of all real numbers. What type of line is this? Horizontal or vertical? Horizontal. All the y coordinates are 5, meaning none of the points rise above 5, so they just sit all across the graph horizontally at 5. Okay? So which one's not equal to all real numbers, the domain or the range for that graph? The range, right? Because the y coordinate is stuck at 5. Okay, so that's one example. All right, somebody else give me a different example. Yes. Good. X equals 5. Okay. All right, so what type of line is that? Vertical, right? Let's solidify the ideas, all right? Which means what domain or range, which one is now not equal to all real numbers with our vertical line? The domain, okay? The x value must be set equal to 5. It cannot be anything else. So the domain is affected and can only equal 5. It can't move anywhere left or right. Okay? Everybody okay with our exceptions here? All right. Okay, on your parent graph. So look at the graph that we made. Okay? What was your x-intercept? At what point did the graph cross the x-axis? Our parent function. So the function we graphed, the only graph we've drawn. 0, 0. Okay? It crosses the x-axis at 0, 0. Where does it cross the y-axis? 0, 0. What can anybody tell me about x-intercepts in general? If I didn't show you a graph, but I said, tell me one thing you know about the ordered pair of an x-intercept, but I'm not going to show you my picture, what should you still be able to know? If it's an x-intercept, what must be true about the ordered pair that defines the point? Good. Okay, so that the x value is going to be the first number is going to be your x-intercept. And what's true about the second number in the ordered pair? Is the y value, what must it be equal to if this is an x-intercept? 0. Who can tell me why the y part must be equal to 0 if I'm calling it an x-intercept? The y has no value. Where does an x-intercept sit? On the x-axis. Is it allowed to move up or down from the x-axis? No. So it's not allowed to have any y value, right? It can't climb up or down. So we know every time that the x value will be some number determined, maybe 0, maybe not, but that the y value must always be 0 if somebody is calling it by the name of x-intercept, right? So somebody define the same thing for me for y-intercept. What would we know about any y-intercept on a graph? 0, y, right? It must be on the y-axis, which means it can't move left or right, so the x-coordinate must be 0, and then y could be any value that we determine. So how would you tell somebody if they didn't have the picture, but they had the equation in front of them, how would you tell them, here's how you use algebra to find the x-intercept? What would you do? So if I have an equation like this in front of me, what algebra do I do to find the y-intercept? Yeah. Good. Okay. To find the y-intercept, it's going to be whatever the y number is when you know for sure that the x is 0. So here, you set x equal to 0 in your equation, and then you solve. And you'll get a y, right? Because your equation only has a y and an x. So then, how do you find the x-intercept? Yeah, set y equal to 0 and solve. Again, so this is like review, but maybe some stuff you haven't seen in a while, so we'll each be kind of at a different space. All right, so the next sentence says, not all lines have both x and y intercepts. Give 2 examples, one for each case. So we want an equation of a line that has no x-intercept and an equation of a line that has no y-intercept. Right, who thinks that they could give me an equation of a line that has no x-intercept? It will never cross the x-axis. Liam? Good. Some horizontal line that's not sitting on the x-axis, right? If it's parallel to it, it will never cross the x-axis. So he said y equals 1. It could be y equals any other number other than 0. If it was 0, you'd have lots of x-intercepts, right? Like the whole entire x-axis. All right, who can give me an example of a line then that has no y-intercept, a line that will not cross the y-axis? John? Yeah, sure. X equals 1, or x equals anything other than 0. Again, those horizontal and vertical lines are the things that are making it different for us. Okay? All right, now before we write the slope part, let me just... All right, so this slope is asking you the slope from your graph. So again, look back at your graph. What did we determine was the slope while we graphed that line? Yeah, 1 over 1, okay, which we'll just simplify to say 1. So in the identity or in the equation you guys originally had, the slope was 1. So that kind of covers all the graphical stuff and how the graph connects to the algebra, but it doesn't cover all the different forms of the equations of the line. So that's the last thing that we have to add. All right, so equations of lines. Okay, formulas for each form. Somebody give me one formula that you know is an equation of a line. Yeah, no. Okay, y equals mx plus b. Okay, and this, so that we know, is called slope-intercept form if we forgot, and that's because it literally gives you the slope and the y-intercept specifically. Okay. All right, someone else give me a different form of a line that you know. Liam? Good. Okay, so standard form. I'm actually going to put standard form on number 3. I have a reasoning for it in my head. tell you why. Okay, so standard form looks like this. And it has like rules attached to it, like A, B, and C must be integers. What does that mean they can't be? Yeah, like no fraction or decimal parts to them. And they want A to be bigger than 0. In other words, they want the first number to be positive. Standard form kind of reminds me of like English grammar rules. It's like one of those things that it's like it didn't really develop because of parts. Like this has actual parts in it, right? It just kind of developed like here's a pretty way to package it and follow these rules so we all write it the same way. Kind of reminds me. All right, what's the third form? Yes, sir. Is there? Yeah, point-slope form. So slope-intercept form and point-slope form, their names are based on the information that you could actually plug into the equation. So slope-intercept, you write the equation with the slope and the y-intercept. Point-slope, you write the equation with a point and the slope. So the way you write the equation is you take y and you subtract some y value from some point that you know. Then you have your slope, and then you have x minus some x value from some point that you know. All right, so if the line is in slope-intercept form, y equals mx plus b, how do you guys graph it? Yes, sir. Okay, so first, graph the b, okay, which is the y-intercept. And then second, what did you say about the slope? Follow the slope, okay. Use the slope from that point. Okay. So you plot your b, then you use the slope from there. You count it. Right? Okay, what if it's in point-slope form? So what if it's in this form? So you're looking at something maybe that says like y minus 2 equals 3 times x minus 5. What information could you pull out from that equation that you could put on a graph? Think about what it's called. What do we know? Yeah. Okay, good. So right away, this is a y value and this is an x value. That's a point on your graph. So point slope and slope intercept are actually very similar. The only difference is here, you start with the b and it's the y-intercept. It goes on the y-axis. Here you start with a point 2. You just have to gather the numbers to make the point. Okay? So you would first graph the point. Okay, so you're pulling out those x1 and y1 values. And then what would you do once you have a point? How did we complete our graph when we had slope-intercept form? We plotted the y-intercept, and then we did what? Followed the slope. So here, you plot a point, and then you can follow the slope from that point again. Your point's just not necessarily on the y-axis, okay? So they're actually very similar. It's just that one gives you a random point and one gives you the y-intercept. How do you like to graph when it's in standard form? I know it's not the most useful form. How many of you, honestly, if it's in standard form, you change it to slope-intercept form and then you graph it? Way to be honest. I know. I do that part of the time too. Okay. Actually, the easiest thing to find in standard form, the only thing that's nice about it, what would happen in standard form if I plugged in 0 for x? Yeah. Let's say I plug in 0 right here for x. This whole term then becomes 0 and unimportant, and I could easily find that y is equal to 3. That means I plugged in 0 for x and found that y was 3. Okay? It's also really easy to plug in 0 for y. If I plug in 0 for y, then this whole term would become 0. How many of you guys remember this in algebra, like the cover-up method or something like this? Yeah, really they were plugging in zeros, right? And then if I have 3x equals 6, I get that x is 2. What did we call these points where you plug in 0 for x or you plug in 0 for y? It is substitution, but what do we call the points that we're getting after we do that substitution? Not the vertex. So the points where either the x coordinate is 0 or the y coordinate is 0. The intercepts, right? So probably the easiest way to graph in standard form, even if you get a weird fraction, like who cares, just plot it about where it goes on the axis, right? Is to quickly figure out these two things. Plot this one on the y-axis, plot this one on the x-axis, and draw the line between them, okay? So probably in standard form, you want to find the intercepts. And then once you find the intercepts, you want to plot them and draw your line. Okay. Is that okay for an overview of each form and just kind of remembering what is it really giving you, what's probably the easiest thing to do with the information? And maybe it will save you the time of trying to transfer everything into slope-intercept form, okay? If you like it and you're stuck, that's a way to do it, but it's nice to know these other things so you don't have to do as much work, okay? All right, I think. Last thing. All right. So there is one linear relation that is not a function. So who remembers the definition of function from Algebra 1 and Algebra 2? Sounds like, yeah? Okay, so what does it mean to be a function? Good. Okay, it can't intersect any x point twice. So you guys remember that little vertical line test you used to run on the graph? Basically, when you run a vertical line test, you're thinking about a vertical line on the graph and saying, does it cross my graph twice? If there's a line on your graph, will any vertical line ever cross it more than one time? For the most part, no, but there's one exception. What kind of line is there that would fail the vertical line test? Now, it has to be linear. So think about our special cases. So as long as it has a slope, a vertical line is never going to cross it twice. Do you have the answer for us? No? Okay, what about a horizontal line? Does it pass or fail the vertical line test? It passes. Every vertical line still only crosses it once. Okay. What about a vertical line? It's supposed to be vertical. It would fail the vertical line test, right? It would be all fine until you drew the vertical line that went through here, and then how many times is that crossing that line? Like infinitely many, right? Okay. So that's because this x value, this input, has lots of different outputs. So the definition of a function was when you put in a number, you should get one number out. But in this case, when you put in this x value, say it's 2, you get out 0, you get out 1, you get out 2, you get out 3, you get all these different values out. That's not a function. Okay? So a vertical line is not a function. And if you want to remind yourself, that's x equals a number for its equation. Okay? All right, and then let's answer the last one. Well, what we'll do is just talk about it for a second, and then you guys can write an example of each. Okay, what does it mean to have a slope of 0? So slope measures like incline, right? So what does it mean to have a slope of 0? It's completely horizontal. It's completely flat. It's like walking across the floor that has no climbing aspect to it, right? So that's having a slope of 0. What does it mean to have a slope that's undefined? Yeah, good. Straight up and down, okay? So steep we can't even measure it, okay? So slope of 0 means we're horizontal. Undefined slope means we're vertical. Notice it says to give an example. So you need to state for yourself what it means. Slope of 0 means this. Undefined slope means this. Give an example of each. That's going to go back to those x equals y equals equations. We already matched up horizontal and vertical, so look back through if you have to. Okay?